All right, everybody. Our topic today is rate of change and slope of lines. So a rate of change is a ratio that's like a fraction, something over something, that describes on average how much one quantity changes with respect to the change in another quantity. So we think of rate of change if x is our independent variable, the one on the horizontal axis, and y is the dependent variable. However much y changes over however much x changes is our rate of change. So as we change a unit in the x direction, how much did y change corresponding to that? So some ways we may think about that or have heard about it is change in y would be the rise of the function on a graph, and change in x would be the run. We also can represent this phrase change in with a Greek letter called delta. So another way to write that is delta y over delta x. Delta is just a Greek letter that we use throughout all of math and science to represent change. All right, so fixed rate of change with a table. This is something you've probably seen before. We have our x value increasing step by step, and our y value here is also increasing step by step. We're going to find the rate of change in each of these. So we're looking at how much our y value changed each step. If we did 152 minus 76, that would be the increase here. And it turns out that is also plus 76. And then from 152 to 228 is another plus 76. So we're increasing the same amount each step here. Our x value is going plus 2 from 2 to 4. And then plus 2 again from 4 to 6. So going back to what we said, our change in y over our change in x, the change in y was 76, and the change in x was 2. So our rate of change would be, if these are, let's actually put units, we have miles per hour. If we simplify this fraction, 2 goes into 76 38 times, so we could call this 38 miles per 1 hour. So we just leave the unit and take off the 1 there. So that's how fast we're traveling, and that would be like the rate of speed you're driving in a car. If you're measuring how far you've gone and how long it took, then we're calculating the number of miles per hour that we travel. So our car is traveling at 38 miles per hour. Same kind of example on B. Our x value is increasing by plus 3 each step. So we go plus 3 and plus 3 again. And our y value is increasing by plus 48 per step. 48 there, and then another 48 there. Same idea as here. We're going to take the change in y, 48, over, and that's square inches. And then on the bottom, we'd have 3 tiles. So if we simplify, 48 over 3 could be written as 16 square inches per tile. So if we're tiling a surface area, each of those tiles makes up 16 square inches. And we've added 3 of them at each step, so our total area has gone up by 48. If a rate of change is constant, then we have a linear relationship. So we just saw that with those 2 examples. We'll look again here. Our x goes up by plus 1, and then another plus 1, and then another plus 1. So constant rate of change for the x, or constant increases step by step. Our y goes plus 6, plus 6, plus 6. So this is what we call a linear function, because for every 1 value we go up in x, we're going up 6 in y very predictably. So on a graph, as we go over 1, we would go up 6, so our graph would look something like that. For B, we have a different step size. So if we go from negative 10 to negative 2, if we think of our number line, we've gone to the right by 8 steps. Same thing from negative 2 to 6, we've gone 8 steps to the right, and then again 8 steps. And as we saw above, we get that by subtraction. So 14 minus 6 is 8. 6 minus negative 2. Remember, if we have minus negative 2, these 2 minuses together make a plus. It's like the reverse of negative 2, or the reverse of the reverse. I think of it like 2 mirrors reflecting back each other to get back your original positive value. So we have 8 there, and then negative 2 minus negative 10. Same idea, this minus minus becomes plus. So negative 2 plus 10 gave us plus 8 here. So think about how many steps you'd move along a number line or an axis, or you can do it as subtraction of the newer value minus the older value. So let's do that again here. We'll look at this. This is 1 minus 5. So our change here is negative 4. Then we have 1 minus negative 4. 1 minus negative 4 is like 1 plus 4. So our change there is so minus 5. Oh, I did it backwards. Negative 4 minus 1. So you take the newer value minus the older value. Negative 4 minus 1 makes negative 5. And then our last step is negative 10 minus negative 4, which is negative 10 plus 4. That gives us a negative 6. So even though our x value is growing at a constant rate, our step size is the same. Our y value isn't changing by the same amount each time. So this is not linear. When it's the same on both, it is linear. And then for our C example, our x values kind of jump all over the place. We have 12, 9, 3, 6, 0. That makes it hard to tell what our step sizes are. So I prefer to look at them in order. And if I go from 12 to 9, that makes a step size of minus 3. If I go from negative 4 to 1, that makes a step size of plus 5. So 1 minus negative 4 would be a positive 5. To keep the step size the same, I want to look now from 9 to 6 is still a minus 3 step size. And I'm going to compare that here to our change from 1 to 11. 11 minus 1 would give us a change of plus 10. So even though we had the same step size between those two, we ended up with different changes in our y value. So again, we could look at 6 to 3 or 3 to 0. We'd see that we're not having the same change. And if any one of these is different, then we don't have a linear function. So we find two different changes where our change in x and our change in y aren't consistent. So we have a consistent change in x, but a different change in y. We know this one is not linear. And I could have, again, looked at 3 to 0. That's a change of minus 3. That corresponds with 6 to 16. That is plus 10. So we need to check as many as it takes to find two that don't match, because we could have some of them match and some of them not. So you see, if we'd only checked 9 down to 6 and 3 down to 0, we would have seen a change of 10 for both of those. So for that part of our graph, it is linear, but the entire thing throughout is not linear. We have an example like that here, where rates of change can vary, and sometimes they could be constant, and sometimes they might not. So looking at this graph, if we picked points from 7 to 6 to 5 to 4, any of those, picking those points and looking at just them, this would look like a linear function because our change is the same. Our rise over run here is the same for all three of these steps. But then if we look at a different step throughout this whole data set, we'll see that they're not all that same one. So back where we were just looking on this chart, we can have some the same, but if any are different, then the entire function is not one linear cohesive thing. So this graph shows the number of catastrophic injuries in cheerleading over 10 years. We have a number from 2001 to 2002, and then year by year we have the count at each year, and you can see that it's not one constant rate of change. So they've asked us to find the rate of change from 2001 to 2002, so that's this data point here. We looked 2001 to 2002, we had 10 injuries. And then 2002 to 2003 is this data point here. Let me pick a different color since that's blue on blue. So we have this purple point and this purple point. And just like we did before, we want to look at the change in y. So that's our rise from here to here. So that would be a change of minus 6. We went from 10 to 4. We would write that as the new point 4 minus the old point 10. That gives us negative 6. And then our change in x's is just plus 1. We can think of this as 1, 2, 3, 4, 5. As far as years, we're just counting our number of years going forward from 1 to 10. So it would be year 2 minus year 1. So we'd get a total of -6/1, or minus 6 injuries per year. So that shows a decreasing trend, right? But if it doesn't continue, or it would keep going down the next year, instead it goes back up. So then we want to look at the change from 2002 and 2003 to the next one. So we're starting again at this point here with the 4, and now we're going to the next year, year 3, where we had 8 injuries. Doing our same thing, we take our new Y value of 8 minus our previous Y value of 4, and we divide by our new year number of 3 minus our old year number of 2. That gives us 4/1, or positive 4. You don't have to write the plus, I'm just trying to show that it's different than the decrease we had. So we went up 4 injuries per year. So very much not a constant rate, right? We went down here, -6 per year, and then +4 per year. So that tells us that neither of those is useful for predicting future values, because the rate changes from year to year. Whereas a constant rate of change over a long enough time would allow us to kind of predict that the future will keep following the same trend. All right, so explain the meaning of the rate of change. So this one, like we said, we have a decrease of 6 injuries from year to year, and then the second one we have an increase of 4 injuries from year to year. Different rates of change are shown on the graph by different angles of slopes. So here where we had -6, notice this is a pretty steep line coming down, and then +4 is a bit less steep of a line going up. So higher rates of change give you steeper lines. So this line here from 7 to 6 to 5 to 4, that one is going to be a lot shallower. So it's a low rate of change because it's not a steep line, it's a very shallow line. So the slope of a line is the ratio of the rise to run. Just like I was saying, it can be used to describe the rate of change. Slope describes how steep a line is. The greater the absolute value, the steeper the line. What that means, it doesn't matter if the number is positive or negative. A bigger number, a further number from 0 in either direction makes a steeper line. So whether it's -10 or +10, those would be bigger slopes than -2 or +2. The positive or negative just tells us whether the line is sloping up for positive or down for negative. So in terms of math, we refer to slope with the variable m. We're going to call the slope m of any non-vertical line through 2 points, the change in y, so again this is the new y value minus the old y value, over the new x value minus the old x value. Exactly like we did in that previous example. We took the new number of injuries minus the old number, and the new year number minus the old number. And that gave us a slope of our line. We're going to do some examples. I'll go through A and B and then leave the others for you to practice on your own. We're going to find the slope of these. I'm going to write our general form that we just saw since it's back on the previous screen. We had our slope equals y2 minus y1, our new y minus our old y, over x2 minus x1. And while you're getting used to this, it's a really good idea when you have two ordered pairs like this to label it. This will be point 1, our -3, 2. That's our old point. Let's label this as x1 and y1. And then our new point we'll label as x2 and y2. That way we're very clear about what goes where in this equation. So both of these are point 1, and remember in an ordered pair we always have x, comma, y. They go in alphabetical order. X comes before y. So let's plug this in. Our slope here equals y2, which is 5. I got that right here. Minus y1, which was 2. So our change in y value was 3. We went from 2 up to 5. That gave us a difference of 3. Then on the bottom we put our new x value, that's 1, minus our old x value, that's -3. Just like we saw before, when we have minus negative, that's the opposite of minus, so it's plus. We're just going to turn those two minuses back to back into a plus. That's similar to when we multiply a negative by a negative, it reverses itself and we get a positive. But with addition and subtraction, what we're looking for is two minuses back to back. So if we had negative 1 times negative 3, that would give us a positive 3. If we had 1 minus negative 3, we would get positive 4. Now, if we had negative 1 plus negative 3, that's a little different. That doesn't change the sign like in multiplication. This is the same as negative 1 minus 3, and since these are both negative and we're adding them together, we're combining them by addition, not multiplication, this would give us a negative 4. So that's just integers and signs. If you're not comfortable with that, be sure and practice. This is a really good unit for practicing when we flip signs and when we don't, and how we combine positive and negative integers. All right, so let's look at B. We're going to, again, look at our slope is our y2. I'm going to go ahead and label x1, y1 for our first point, x2, y2 for our second point. We're going to follow this formula again, y2, negative 8, minus y1, negative 4. And we're going to divide by x2, that's negative 2, minus x1, that was negative 3. Again, anywhere I have minus negative, those two basically cancel out and become a positive, and the same thing down here. Now that I've resolved these double signs here, I can go ahead and combine them. So negative 8 plus 4 equals 12. Negative 2 plus 3 equals positive 1. So our slope on the second one would be 12. I don't think we ever finished the first one. We had 5 minus 2 was 3, over 1 plus 3 was 4. So our slope here was 3/4. Remember, if we relate that to our graph, that's our rise over our run. So every time we go to a new step, we go up 3 over 4. Here, our slope is 12, and again, this is our rise and our run. So we're going up 12 every time we go over 1. So this line is much, much steeper than this line. If we had a graph, the 3 to 4 would be something like, up 3 over 4 would be something like that. And then our up 12 over 1 would be something like this, very, very steep, because every step we go to the right, we're going up 12 steps this way, so way, way, way up. So that's where we were saying bigger numbers give you a steeper slope. All right, so you can practice C through H here on your own. You can pause the video if you want to take a minute to practice those. And then we'll go down to an advanced use of the slope formula is to find a missing x or y coordinate. So here we're going to give you a different piece. So we're going to use the same formula, m equals y2 minus y1 over x2 minus x1. Instead of looking for m and having all four of these values, we're going to be missing one of these four values, and we'll have the slope and the other three. This is where the work we did with literal equations comes in really handy, because we need to rearrange this one to solve for a different number. All right, in this example, we have x1, y1, x2, y2, and then our slope, m. We'll plug in the things that we have in this formula. So m is 1/2, and we're going to say equals, we're just following this formula here, 1/2 equals, then our y2 value is 2, minus our y1 value was 3, and then we divide by our x2 value. That one's a variable, that's the thing we don't know, but they say it's r, so we're going to put r there, minus our x1 value, which was 6. So now we need to solve this equation in order to find r. We'll simplify and collect our like terms up here first. So our first step will just be to rewrite this equation with these 2 and negative 3 collected. So I'm going to rewrite that as 1/2 equals -1 over r minus 6. Since we have a top and bottom on both sides of our equation, we could go ahead and cross multiply here. So I'm going to multiply 2 times -1, and I'm going to set that equal to 1 times r minus 6. Writing that down, I have 2 times negative 1 on one side, and 1 times r minus 6 on the other. If I just put those together, 2 times negative 1 is simply negative 2, and 1 times r minus 6 is just r minus 6. Then to finish solving, I need to move this 6 to the other side. So we'll do an opposite operation to do plus 6 on both sides. And finally, rewrite our equation. R is all by itself. I'm going to set that equal to negative 2 plus 6 would be 4. So that tells us that our missing point here was 4, 2. That would have been the ordered pair. All right, going on to the next one, I'll go ahead through another example of this because these are a little more involved. We're going to do the same exact formula again. This time our x1 is negative 2, y1 is 6, x2 is r again, and y2 is negative 4. Our slope m is negative 5. So our initial equation is negative 5 equals y2 minus y1 divided by x2 minus x1. We see a minus negative here, so again we're going to change that into a plus and get rid of that double negative. Okay, we wanted to cross multiply as our next step over here, but we don't have a denominator, so we have a couple options. One, we could put over 1 and then we could cross multiply. But our other option is we don't really need to cross multiply, we just need to multiply both sides. So what we're trying to do is get this r plus 2 off of the bottom because we can never have a variable on the bottom of a fraction. So this r plus 2 is all one unit together. We can't separate those two things. They're a combined unit right now because they're both under this dividing line. And in our order of operations, dividing comes before adding, so these two are stuck together. What I'm going to do is multiply both sides by r plus 2, that whole unit together, which is just like if we cross multiplied the negative 5 times r plus 2, right? That's the top and bottom. And then I'm going to rewrite this one. I'll put the negative 5 in front because when we write a factor times a parentheses quantity, we usually write the constant out front like this, negative 5 times r plus 2. Equals, and then on this side I had negative 4 minus 6, that's just negative 10. As a next step, I could distribute the negative 5, but if we notice that this coefficient here and this constant are divisible, we can go ahead and divide out the negative 5 from both sides before we worry about distributing. So now I can cancel the minus 5 and just bring down r plus 2 equals negative 10 over negative 5 equals 2. As my last step, I need to get rid of this plus 2, so we're going to subtract 2 from both sides and bring down r equals 0. So that's not the same as there's no r, that literally means r is equal to 0. So our point that we were missing here, our second point, would have been 0, negative 4. So when y is negative 4, our x value on our graph would be 0. So that's how we solve those kind of problems. We can do the exact same process if we're missing x1, y1, or y2. It's a little easier if we're missing one of the y's because then our variable's already on top. We don't have to deal with the idea that it's on bottom. But very similar process no matter which one of those we're missing. So these are homework. These are similar to the problems that we've been doing. You should be practicing some of these. So you have ones where you're calculating the slope. I think all of these are slope calculations. Yes, so these are all slope calculations. And notice that it says we want to leave our answers as fractions. So we don't want decimals here. We always want to express slope as a fraction because we want to think about rise over run. So if I gave you the slope, so if I said the slope is 0.75, that's a lot harder to think of in terms of graphing than if I told you m is 3 over 4, which is the same, but now we can clearly see that if we were graphing, we have a rise of 3 and a run of 4. So the fraction translates a lot more easily into graphing than a decimal does. So that's homework. These are other ones where you're looking for, are these linear, and if so, what is the slope? So again, we're looking at change in x, change in y, same kind of thing. All right, so that is it for today.